Here we are with the Unit 3 full overview. And as you can see, this unit right here is about 6 weeks long, themed on energy and engineering with a bungee jump. It takes on two critical, really big performance expectations around creating a computational model to calculate the change in energy flowing through a system, and then using a computer simulation to model the impact of proposed solutions on a real world problem. You can see here also several assessment opportunities. Right, to situate it in the whole year, let's zoom into the timeline. And again, you can see what patterns are reoccurring here in the energy and engineering unit, and then also the whole year at a peak in 0 in GSS file. And again, so you're starting to see that the performance expectations are increasing, and these are big ones. These ones take time to develop and lay the groundwork to increasingly take on more performance expectations in each unit. Okay, zooming back out, looking at our storyline progression, this is themed on a bungee jump. So they really do a bungee jump. This is something that even years later, students say something they remember in one of the best days in physics. We'll talk about that more towards the end as we come up to that task. So I'll just say with that launch, we go through, and I'm going to give just the 20-second overview, and then we're going to go through each one. So one of the first things we have to do is learn to track energy. And then just like in Unit 2, we're upping and spiraling back to getting really good at developing a system analysis. So really creating the map, really. So we're actually going to leave the progression arrow and start to use the system analysis so students know exactly what's coming next. One of those first things coming next is needing a model for gravitational potential energy and kinetic energy. That's a good one. And then for this storyline, we also need the mathematical model for elastic energy. And then we'll use the models that they create to code an app that tracks the energy flow in a bungee jump and correctly predicts how much string to add for a successful jump into the target zone. All right, so that all brings us to the essential question: how can we use STEM to make thrilling experiences safe? All right, so we get a lot more specific about engineering now. So Unit 2 did introduce this, but we're spiraling back and really upping the game. So here they do analyze several different engineering cycles. And then for this unit, we use this particular one and we change it up each unit. All right, so in any case, they do need to get clear on what they're actually trying to solve. Here is that example. We as app developers seek to create a user-friendly application in order to create a thrilling, safe bungee jump ride for Oaks Park. I'll just show the quick phenomenon video. If you like it, you can use it. The world records for like longest distance. All right, so you can watch that a few times, just like the video in texting and driving. Students then step back and think about, what are the driving questions? What do we need to do? So, you know, think along the lines of make it, bake it, take it with the pizza, or distraction, reaction, traction. But this is a chance to go a little bit different. They can map out a lot of this unit. So what are our driving questions? So they each get a few sticky notes. And then what's one question, or we have them come up, each student comes up and checks with their table group so that we make sure we get a variety. But what as scientists or engineers, do we need to know to investigate and model to make this jump successful? And this is such a great time to get some student leadership. They can be organizing this, clumping them on the board, and then every couple of days you can cycle back and see how much we're following their plan and answering the questions that they came up with. All right, then we're on to tracking energy. So there's several videos, 4, 5, 6 videos they watch. We'll just watch one quickly. So you can see there's a lot of elastic energy gets turned into kinetic, and then ultimately gravitational potential energy, which is sort of the reverse of a bungee jump. And through all of those examples, this oftentimes is review of middle school. We come up and we also use the energy skate park FET, which students have oftentimes seen in middle school as well. So that's just a one-day activity and really just primes their brain with the law of conservation of energy. So we quickly pivot that they track the energy. Now that they got that skill, they track the energy, but really annotate. This is covering it. Like, for instance, when the jumper is getting ready to jump, we know that they have a long way to fall, so they got a lot of EG. And then look, over here, the bar is full EG. And then we even get them to explicitly say, okay, how did we about to jump? So they're not moving. So EK is 0. The cord is not stretched. So E elastic is 0. That's what we mean by annotate. Mark this up. And then these loopy arrows are energy transformation. So gravitational energy transforms into kinetic. Block arrows that leave the jumper system and go into the cord is a transfer of energy. Those are specifically called out for in the evidence statements of the NGSS. So once the movement of the jumper starts to stretch the cord, that's a transfer of energy. But of course, the total energy is always conserved. And of course, the NGSS in one sentence is use the big ideas of science to explain phenomena and solve problems. Here we're using it to explain phenomena. So they explain the basic physics of a bungee jump. So you can see they use the tools of science to explain science. So here we have energy bar charts, and then they just explain their annotation. If you look, I'm looking at the answer key here. They lead with their most important sentence, the most important big idea, and that, of course, is conservation of energy, and then just walk people through your annotation. So use the tools of science as a pre-writing strategy. That's what we're seeing here, and with really good results. All right, then we move on and go a little deeper into the request for proposal. This is meant to be a technical writing. It's meant to feel overwhelming at first, but take big problems and break them down into more manageable. So let's just take it, section by section. And then there's a lot of things for the bungee cord. It needs to be able to, you would fill these in for your school. That's why there's these green input spots. And it has to be a certain length, and there's a target zone. It's not a competition to get closest to the floor. That does not set students up for success. So we choose not to do that. Sometimes that's more fun. It turns it into a competition. And but that's not so often what engineering is about. It really is about a target zone. Then they step back, and just like in texting and driving, we give them some of this structure, but they really have to figure this out. So they make a system analysis. How do they get all of those things that they need from the engineering portfolio? And then that guides their learning. So, with texting and driving, we started from the top and worked our way down. Here, we're going to start with the upper left and just work our way through these. And so that, oh yeah. And again, just like texting and driving, we want this system analysis to really work, to really mean something to students. So that means we got to slow down and spend some time on it, get it stronger and clearer for them. And students start stronger and clearer going, oh, I'm so confused. And end feeling pretty good. Now, if they're truly confused, you probably don't want to start stronger or clearer right yet. So you might want to slow down and do make sure they're making sense of that. But stronger and clearer really does move them to better understanding the system analysis. Okay, so first up, we can just see is we got to figure out the math. We know that all the energy starts as gravitational, but we need a number. How, what is the mathematical model? So there's an activity where, cultivating their inner scientists, they're thinking about walking the triangle, moving between mathematical representations and what they know. And I'm just going to scroll through this quickly. There's just some guided, think almost like POGIL-like activity, and guiding them through to figure it out. And then they do some graphing and Desmos for kinetic energy. Okay, so now that we have that, all right, a lot of these other things are things that you just need to literally measure, like with a tape measure, starting height, go to wherever you're jumping at your school and measure that. Then we need the spring constant and the distance the cord will stretch. We need the model for that. That model requires us to have the model for elastic energy. So of course, you can guess what's next. We're going to do a lab on finding the mathematical model for elastic energy and jumpers, and we are going to have an analogous system of study, as we so often do, and that's just really stretch cord and some weights. And we're going to do system analysis. We really spiral back to system analysis again and again. We have it for the whole jump, and then we have it for this lab. In fact, after they hold a mass with the cord taut, they let it go, it goes to the bottom. And so again, it starts all gravitational. Some transforms into kinetic, and then of course stretches the cord, transferring it to the bungee cord, that then as it stretches immediately transforms it into elastic energy. So all of the missing gravitational at the bottom where it's no longer moving, we know must be an elastic energy. So we know elastic energy is the gravitational starting minus the gravitational ending, which they can go down and code. I'm showing the answer key. Students go and code this, and if they're having a trouble with this, or it's not making sense, or it's a day you have a sub, there's a video that walks them through every little piece. But a lot of students can go from the system analysis to the coding. Not everyone, you're always going to have some students, but if it's low enough, you can go and work with them individually, or if it's a big group of the class, then do it as a whole class activity. All right, and then after they collect their data, they find that pattern, it's quadratic. And of course, we, with some, exploration, similarities and differences, and the card sort, I'll just say is right here. Then it's in the model, it shows up as the number in the graph, it's the curvature of that parabola. And in the real world, it has to do with how strong that cord is, the spring constant. And we expect it to be quadratic because as you stretch it, you're stretching it over a bigger distance. And as you stretch a rubber band, the force needed gets bigger. So we always see that two-dimensional effect when we have a quadratic. So as the distance increases, two things are happening. You're pulling on the rubber band for a longer distance and with more force. So it shows up twice. That's also why we like to write, instead of distance squared, distance times distance, to make that conceptual idea more explicit. All right, so with that, we've really, there's a little experiment to figure out the spring constant, Hooke's law, very typical, stretch it a bunch of different distances and look at the slope. So we have all of the pieces together, so we can now actually code them. And look at this, it looks a lot like our system analysis, except for the jumper was in the middle, but it was judicious to do it for the coding to have the little diagram on the left. And you can just see all the inputs and outputs. Again, 3 different levels with video tutorials for each level. And then they auto-generate the energy bar charts throughout, just as specified in the engineering portfolio. Then also one of these last quizzes, and this is assessment for learning. So claim evidence reasoning around troubleshooting and error in the bungee jump. And these are selected because these are the 2 most common ones. And we do want to assess and give feedback to students on their ability to troubleshoot, such an important skill. So they either mismeasure the mass, and then they can tell from the cord stretches further. If it's the mass that was mismeasured, they can argue using their simulation what happened, or what happens if it was the spring constant that was mismeasured. And so they do claim evidence reasoning around that. Just a nice touch. And then we have jump day, super fun. This is a day you can invite parents, or oftentimes more administrators or other teachers in the buildings, or just other people in the community that are willing to come and listen to students. There's a lot of scaffolding. So there's pre-made interview questions for the adults. There's a peer evaluation of teamwork that the students do for each other. And then of course they finish their bungee jump engineering portfolio and submit that. So a lot of structure there. There's also some fun awards and signage for the jump day, just to make a big deal out of it. It's just sort of, just all meant to be fun. If you do have extensions, it extends into a second day and some groups need an extension. Here's a redesign because there's too many ankle injuries that front load some ideas that are coming next unit with impulse and momentum. And then that completes our arc. But I do want to say in unit 5, they evaluate published materials. And we really, because there's a performance expectation around, does electromagnetic radiation evaluate published materials around electromagnetic radiation, think like power lines and cell phones, do they cause cancer? And we want students to really be at the mastery level, but students don't walk into unit 5 at the mastery level. So exposure, practice, mastery. So this is the exposure and some practice here in unit 3. Some people do move it to the end so it doesn't break up the unit storyline. If you do look at the teacher calendar, though, we do suggest putting it mid. It's a nice break, and it really is just like a half hour, just so important. And it's they look at 2 different viral videos. Here is obviously an advertisement for shoes. How about how they can run on water? Really well done, and you can just see there's also even a behind the scenes of the filming it, and just a nice touch at helping students evaluate viral videos and published materials. All right, with that wraps up our full overview of Unit 3.